and its no load power factor is cos phi 0. These two things, phi 0 and I 0, phi 0 is the angle, so that cos phi 0 is the no load power factor and I 0 is the no load current. These two data we require, and also from block the test, short circuit test, we take the short circuit current, ISC short circuit current, and phi SC, where cos phi SC is the short circuit power factor under block rotor condition. These data are taken. Then another thing is ISC and block rotor current, ISC short circuit current and block rotor current must be converted to the rated phase voltage. It is important because in short circuit test or block rotor test, we don't apply rated voltage. The motor is not allowed to rotate. Okay, by blocking the rotor. By blocking the rotor, we don't allow the motor to rotate. If the motor is not rotating, there will be no back EMF. Okay, without speed, there will be no back EMF. If back EMF is not there, then that means with a little voltage, you will make a large current to flow. Okay, and for the motor, and the rated current should not be exceeded. Rated machine has a rated current. Maximum we can go to 120% of the rated current. If rated current is 100 ampere, we can maximum apply 120 ampere, not more than that. 20% overload we can do, not more than that. So, for under short circuit condition, to get the rated current, we require small voltage because it's short circuit condition. So, what? But for circle diagram, we want the short circuit current and rated voltage. We want. So, how to do? For example, we are doing short circuit test, block rotor test, short circuit test of block rotor test. For if a voltage V, I am writing, we have applied a voltage VSC, short circuit voltage VSC, which circulates the current, ISC, which is the full load current. Full load current is circulated. VSC is not the rated, it is very small compared to the rated voltage, but we have to find short circuit current at the rated voltage. The short circuit characteristics of the induction motor is like this. So x-axis is the field current and the y-axis is the short circuit current. And short circuit characteristic is a straight line. This is the short circuit characteristics. It is a straight line. Okay. So suppose this is the full load current IFL, and to get IFL we apply this voltage, that is VSC. Okay. And this is the rated voltage. This is the rated voltage. So if we apply the rated voltage and block the rotor, how much current will flow? We can determine by this straight line. So what is that current? This current I am writing, say I short circuit at nominal voltage. I am writing N. Some symbols are there. N means nominal voltage, rated voltage. So this current is I short circuit at rated nominal voltage. So what is ISCN? That is equal to VR. No, this is sorry. This is the x-axis is the field current. I have written by mistake this VSC. This is not VR. Rather, this is the field current. The x-axis is the field current. This is the case when voltage is VSC, and this is the condition when voltage is VSC. What I have written V rated. I am writing V rated. V rated I am rated voltage. At rated voltage, this much is current. So what is the short circuit current? Voltage is V rated by this voltage here is VSC into current is IFL. Straight line. Basically, it is a straight line passing through origin. Straight line passing through origin. So proportional. So to get full load current, we apply a voltage VSC which is less, and if we apply rated voltage V rated, the current will be ISCL, straight line. So V rated, this is the formula.
Actually, mic is recording which is mic.
অসুবিধা হবো তো এবার খোলার বেলা আছে এটা ইনকনভিনিয়েন্ট হবে
ছোট পিলা ସେ ଯୋଉ ସେଇଠି ତା ଉପରକୁ ଥିଲା
okay, this is the formula. The straight line formula. So this way we compute short circuit current at rated phase voltage. Then, so the steps are mentioned here. So, how to draw the circle diagram? These steps are mentioned here. To draw the circle diagram, we start with this. We start with a vertical axis. Vertical axis will be represented voltage. Voltage anything, we just write it, draw a vertical line. And then we draw the no load current. For example, this is the no load current I0 to the scale. To the proper scaling, current scale, we draw current I0 at angle phi 0. Where cos phi 0 is the no load power factor. In the voltage axis, we make an angle phi 0. Y axis is the voltage axis. Y axis is the voltage axis. With the voltage axis, with respect to the voltage, no load current is lagging by angle phi 0, so that power factor is cos phi 0. So we draw the current phasor like this. Then we draw a short circuit one. So this current ISCL, short circuit current at rated voltage. This one, short circuit test, this current, short circuit current at rated voltage, and corresponding angle is phi s. Draw an angle phi s and draw the vector of ISCL like this. After that, we join these two. This is OA. OA is representing the no load current. This is OB. OB represents short circuit current. Then we join this A and B. Join A and B. Then A and B, we draw the perpendicular bisector. A and B, we draw the perpendicular bisector to A and B. We find out the middle point of A and B, then draw 90 degree and extend it to both sides. Then we draw one horizontal line like from point A. Point A, we draw a horizontal line perpendicular to voltage vector. It intersects this perpendicular bisector of AB intersects at a particular angle. Particular point. That particular point is center of the circle. Then we draw the circle like I will draw it again. Actually, one thing. Angle phi SC will be less than phi 0. Cos phi 0, no? If the angle is phi 0 is 0, power factor is 1. If power factor is 0, then angle is 90 degree. So short circuit power factor is better, more than no load power factor. no load power factor is small. No load power factor is small. So angle phi 0 will be larger. So if that data actually, if you take the data, you will not have this problem. That is the, so I am redrawing it. So that from the origin, we draw the no load current I0, OA. OA is the no load current I0. This is at angle I0. Then we draw OB. OB is the short circuit current and rated voltage. Then we join A and B. Join A and B and draw perpendicular bisector of A and B. Bisector, middle point and bisector. Also we draw a horizontal line from A. So the intersection of the perpendicular bisector of AB at the to the horizontal line is C, where C is the center of the circle. Now we see A as radius. We draw a semicircle that will pass through B also. So this is the circle diagram. C is the center of the circle. A is the radius. CB is the radius. We draw it. And AB perpendicular bisector we draw. Is it clear? First, how to draw the circle diagram? Computation is next. So this is the process to draw the circle diagram. Draw the no load current OA at angle phi 0 with voltage. Then draw short circuit current OB, which is at the rated current, rated voltage. OB is the short circuit current at the rated voltage. And draw one horizontal line from A point A. Then draw the perpendicular bisector of AB. It intersects the horizontal line at point C.
So that OA and OC are one single straight line or
No.
AC?
OA is at angle phi 0. This is a point D. AD is perpendicular to voltage line. AD is perpendicular to voltage line. This is the process to draw the circle. Then how phi 0, phi B are drawn? These are the calculations. That is simple. No load power is √3. No load voltage into no load current into no load power factor cos phi 0. That is W0. From that we get cos phi 0 and phi 0. Then from the short circuit, the voltage is VB, current is IP, and power is √3 VB IP into power factor cos phi. You get the block of the power. Then we will join AB. This is listed. I think you will get from any book. That is not a thing. We join AB, which is AB is called the output line. This A and B joining the open circuit point and current is T, short circuit current T. That is called the output line. Then draw a horizontal line AF. So it is written AF. I have written here B. Then draw perpendicular bisector. I am writing AF. This is AF is the horizontal line, and draw the perpendicular bisector of the output line that intersects at point C or O, whatever. Then O is the center of the red. This is how circle diagram is done. Now circle diagram is written. The next point is here it is given how to get the divide the loss. Point B represents the short circuit current N. Okay. So if you draw a line perpendicular to line like this, which is parallel to the voltage line, we draw from point B a line whose voltage is parallel. So this line, suppose this point is D, cutting the horizontal line. And this point is, let us say, some point dx. So what dx represents? So dx is also equal to MC, because both are part. So dx represents no load loss. Dx represents no load. And Dt represents total I square R loss. Under short circuit condition, there will be some no load loss plus short circuit I square R loss. No load loss is Dx and short circuit loss is Bt. Then short circuit loss has two parts. Short circuit means I square R loss. I square R loss in the stator and I square loss in the rotor. So we divide Bt by at point P. E is the point where BE by BE by DE equal to I square R loss in rotor BD divided by I square DE is the I square loss in stator. Stator or stator? There is a point. Stator, static armature. When it is stator, it can be also confused with starter. Starter, which is used to starting the motor. So starter is not the starter is okay. Starter means for starting. And telling this starter means it may confuse with starting. So we tell stator, stationary armature. So Bt is the total I square R loss in short circuit condition. So it is divided at point E, where BE is the BE by DE equal to I square R loss in the rotor divided by I square R loss in the stator. So then we join AE and AE is the top line. AE is the top line and AD is the output line. AP is the output line. Okay. AE is the top line. So that part is done. This is just repetition, no load test, dog test. Step 2, step 3, step 4, step 5. These are all repetitions.
So we know the local purpose of
Okay. So you see, under short circuit condition, no load current is negligible because you are applying small voltage. So all the current is nearly equal to short circuit current. So I square R loss. So I is common, it is cancelling. So rotor resistance by stator resistance. Rotor resistance, stator resistance are determined from the text.
yes.
We know determine. So rotor resistance, stator resistance. So this is the resistance ratio. Then another point is full load point, speed and full load speed point. Now this vertical line from this D, E, B, you extend it to this side. Okay, this side. We get the point. Just let me go to how to get the full load speed. Full load. This is what? P is the point representing full load point. So how to draw the full load point? It is given written here. Draw the parallel to the output line from B to meet the point at P. From at point to from B. Parallel point, output line, na? Output line from B. B is there. It is the line. P is the full load point. Locate full load point from full load point from B dash. So that so starting from this point X, dx is the no load loss. Dx is the no load loss, constant loss. Then DE is the I square R loss in the stator. Then BE is the I square R loss in the rotor. Then machine has a full load power point. On that full load power point, we to the scale, we draw it here, full load power point to the scale. That point is B dash, full load representing the full load point, and from B dash we draw a line parallel to the output line AB. Okay, from B dash we draw a line parallel to AB, and this point is P, that represents the full load point is P, and OP is the full load current, and this is the full load power factor. Otherwise, it's from the machine.
B dash tangent or
It is parallel to AB.
AB. It is tangent at that point or
Tangent is tangent. Tangent will be tangent. Or another thing can be done. So if we know the rated current of the motor, full load current of the motor, and we can we determine the full load power, rated power. From that we get full load power factor cos phi L. So we can draw OP is the full load current, which is at an angle phi with the voltage. So that cos phi is the cos of cosine of this angle is power factor, and OP is the full load current. Okay. OP. So it will be definitely on the circle, obviously, because full load point will be on the circle. From P, if we draw a tangent to the circle, it will be B dash. That will also can be done. Then same thing. So this is how circle diagram, and from circle diagram we do different calculations. Next we will discuss starting mechanism, starting arrangement, starters for the induction motor. So first one is direct on line starter, DOL starter. Direct on line starter means you are directly switching the motor to the line, direct without taking any effort to reduce the starting current. We directly switch on the motor to the line, direct on line. So basically there is a direct on line starter is coming, and there will be only switch on and off mechanism, switch on and off mechanism. To start the motor, there are so many direct online starter. To start the motor, you push the button, and to switch off, you push up another button. Machine will start and stop. How the starter was, that is mentioned here.
Here it is delta connected. Stator motor.
Machine is delta connected. You don't have to bother about that. Starter machine is delta connected. Normally, induction motors are delta connected. Most of the induction motors are delta connected. Still star connected motors are there, but it doesn't matter whether motor is star connected or delta connected.
It is squirrel cage.
Here it is squirrel cage. So you have what we have. We have the three terminals of the motor. These are the three terminals of the motor. From between the three terminals of the motor and three supply terminals, we connect the direct online starter. So the direct online starter has an on button, push button for switching on, and a push button for switching off, on and off. So basically there is one no good coil, so which makes the movement, the contact, which makes the contact or breaks the contact. This is the no volt coil, and with this mechanism, either it is short circuiting this point or open circuiting, that is contracted by coil, no volt coil. And then there is overload relay. Starter also has overload relay. If the current is exceeds a particular value, the relay will also switch off. That is what. So all these things are mentioned. These are not so much related, not required. So this is the equation. Sometimes you have to do some analysis. The analysis is here. To remember some basic analytical equations. Some equations gives analysis of the induction motor. In induction motor, power transfer to the rotor. Power transfer to the rotor via air gap is called air gap power. Air gap power, that is PG. Air gap power, that is 3 rotor current is I2 square into R2 by S. R2 by S is the resistance, and the current is I2 square, so I2 square R2 by S is the, or I2 dash square, you can write I2 R2 or I2 dash R2 dash, something. So this is the air gap power. Out of that, rotor copper loss is 3 I2 square R2 or I2 dash square into R2 dash. That is equal to slip times the air gap power. If you take slip to the opposite side, it will be SPG, that will be rotor copper. Then mechanical power. Okay. Mechanical power is air gap power, which is the input minus rotor copper loss, speed. So 1 minus S into air gap power. And speed omega m, that is 1 minus S times synchronous speed. So what is the torque? TE, that is mechanical power by omega m. Torque is power by speed. So power is 1 minus S times PG, and speed is 1 minus S times omega S. So PG by omega S. So you can write TE, if you use the power equation here, 3 by omega S into I2 dash square into R2 dash. This is the power torque in Newton meter. Torque in Newton meter. I2 dash by S is there. No? By S is there. S. So we are discussing also starting if slip equal to full load slip. S is the full load slip SFL, rated condition. Then TFL torque is full load torque, that is the rated torque, that is 3 by omega S. Corresponding current is IFL, full load current square into R2 dash by SL. Here you can remember I2 dash is nearly equal to I1. If you neglect the no load current, I2 dash is nearly equal to I1. This is the fact. So this is also the full load torque in terms of rated current, full load current, and if slip equal to 1, that corresponds to what? Starting. Slip equal to 1, then we have starting torque equal to 3 by omega S. Instead of full load current, we write starting current IST square into R2 dash, starting slip is 1. So then that equation which is derived here, starting torque by full load torque, the ratio. Let us find the ratio of starting torque by full load torque. So here 3 by omega S cancels. So it is I starting by I FL whole square to here into here slip is 1, so no problem, and here the denominator is there, so into SL. So that equation is derived. This is what. Another thing is, this is what? This equation. When we direct on line starting, at the starting current, what is the starting current? Starting current is, let us say IST, that is equal to short circuit current, because at starting condition slip equals to 1. Slip equal to 1, this is short circuit current condition. So starting current is ISC with direct on line starting. So now with direct on line starting, you can replace the starting current IST by ISC. That is done here in this equation.
ISC nominal or
It is ISC nominal, not the rated voltage, because if you directly switching on to the rated voltage, so ISC nominal means rated voltage of circuit current. Then starter resistance or reactance starter. So direct on line starting has a problem because with direct on line starting, at the starting point the back EMF is 0. Back EMF is 0, so it draws more current. So around more than 5-7 times the rated current. So machine may not be able to tolerate that current. That current can be damaging. But if the machine is small or up to less the little smaller machines can be started directly on line. Below 1 kilowatt. Small rating machines can be directly started on line. If the machine rating is more, then the starting current will not be tolerable. Small machines are started directly on line. So bigger machines require other starting mechanism to reduce the starting current. What are those techniques? First technique is starter resistance or reactance starter. So in this technique, we connect 3 resistances rheostats. 3 rheostats like this, and these reactances should be equal all the time. So what happens when at the starting, when the machine draws current, a part of the current will be part of the supply voltage will be dropping across this. Voltage drop across resistance is IR drop. So there will be IR drop across the resistance. So if the voltage drop, there is voltage drop across the rheostat, then voltage available to the machine reduces. because whatever supply voltage minus voltage drop in the resistance rheostat equal to voltage available to machine. So voltage available to the machine reduces. Okay, so machine current, starting current reduces. But thing is, as the machine speed increase, because there will be losses, there will be I square R losses in this winding. So as the machine speed increases, back EMF increases, so gradually current also drawn by the motor reduces. So for that, the resistances are gradually cut out. So that rated voltage is so after the machine starting to a transient is over.
This is large machine, a large rating machine, and it is star connected or delta?
Mostly delta connected. Maximum machines are delta connected, but some machines also star connected is there. But the starting mechanism is independent of whether star connected or delta connected. What is the only terminal there between the supply terminals and the motor terminals? You connect the star. So star connection, delta connection doesn't matter. One thing, another point is, in place of if you put resistances, obviously there will be I square R losses in the resistances. So which is a great disadvantage. To eliminate this disadvantage, the resistances are replaced by reactances, inductive reactance, inductors. So in inductors, same process, we vary the the key so that the inductance is partly cut out, slowly cut out. Okay. So the resistances are replaced by inductive reactance. So same thing with this, when we allow a part of the voltage to drop across the starting resistance or starting inductive reactance, then voltage applied to available at the machine reduces. Suppose machine reduces by factor X. That means machine voltage reduces to XB. Obviously X is less than 1. Instead of applying rated voltage, we apply the voltage XB. Okay. If we apply XB, then machine current will be also reduced to X times the starting current. Less voltage, less current, so current reduces. But the thing is, when the voltage is reduced by factor X by the starter, the current reduces by factor X, but torque reduces by factor X square, because torque is proportional to square of the current. Torque reduces by factor X square. So that this is a major disadvantage with this, because though we are restricting the current, starting torque becomes less. X is less than 1, so X square is still less than 1, so reduces significantly. So that is a problem. But still, all fan motors are driven by this. I have similar means previous fan starters you have seen. They are basically inductive reactants. Previous big regulators, fan regulators, they are basically inductive regulators. Single phase. Actually, the single phase induction motor theory is an extension of the three phase induction motor. Discussing about three phase induction motor, same thing can be extended to single phase induction motor. Fan motors are single phase induction motor. Okay. So if you have seen the previous older fan regulators, they are bigger type. They are basically inductive reactors. Same thing. This is same thing. Then another starter is star delta starter. Star delta starter means we starting with star and then changing to delta. Most of the induction motors are delta connected. Okay, some are star connected, not all. So some of them are star connected, but maximum induction motors are delta connected. Particularly bigger motors, those which are delta connected, To reduce the starting current, they are connected in star. At the time of starting, machine is delta connected. First thing, machine is delta connected for normal running. Then all terminals are available. There are three windings. For three-phase induction motor, there are three windings. Each winding will have two ends. Starting end, start and finish. Start and finish, two ends. So all six terminals, three windings will have six terminals. All six terminals should be available to the outside. If all six terminals are available, then at the time of starting, they are connected in star. So then after starting process is over, they are changed to delta. So let us consider in suppose machine is delta, when the machine is delta connected, voltage is V rated, V are for V rated. Then machine is delta connected. So what is phase voltage under delta connection? Phase voltage equal to same thing, rated voltage you are applying the phase. So V phase equal to VR. Now when we connect the same motor in star connected across the line, then same VR we are applying. What is V phase then? This is for delta connection. For the star connection, phase voltage equal to VR is the line voltage. I am saying line voltage. So this is for star connection. That is 1 by root 3. That is by mistake it is written. It is 1 by root 3. 1 by root 3. So in star connection, phase voltage is line voltage by root 3. That is rated voltage by root 3. So thing is, if we are starting with star connection, we are reducing the voltage by factor 1 by root 3. 1 by root 3 is how much? 1 by root 3. Whatever. So instead of applying rated voltage, in star connection we are applying 1 by root 3 times the rated voltage. So we are already reducing the voltage. There is no, in the previous method we can change smoothly, but here is only one change. We are applying 1 by root 3, then we are changing to full voltage. So in between we have a process to start with reduced voltage, that is 1 by root 3. Then that is not over. With star connection, we have applied VR by root 3. What is the starting current to this? Starting current is voltage by impedance. So that means it will be 1 by root 3 times normal current. 1 by root 3 times current becomes 1 by root 3 times, because voltage becomes 1 by root 3 times, current becomes 1 by root 3 times. But in delta connection, what is the line current? Root 3 times. So in delta connection, line current is root 3 times phase current. But in this case, star connection, starting current drawn from the line, starting current drawn from by the line equal to phase current, because in star connection, phase current, time currents are equal. So starting line current equal to 1 by root 3 times phase current, because it corresponds to this voltage. So in star connection, voltage is 1 by root 3. So corresponding current is 1 by root 3. And when you change to delta, voltage will be rated voltage and current is root 3 times. So how many, by what factor current is reduced? 1 by 3, 1 by 3 root 3, because line current, phase current is reduced by the factor 1 by root 3, but line current is reduced by the factor 1 by 3. This is the thing. After start, during running, we are changing it to delta. So what advantage we get? The line current is reduced by factor, the phase current is reduced by the factor 1 by root 3, because voltage is same thing, but the line current is reduced by the factor 1 by 3. And what about the torque? Torque is proportional to square of the current. Which current? Line current or phase current? Phase current. So torque is proportional to square of the phase current. Because phase current is 1 by root 3, torque will be also 1 by 3. 1 by 3. So starting torque is 1 by 3, starting current is 1 by 3. So that is the advantage. The previous method, if we reduce the factor voltage by 1 by root 3, torque will be reduced by factor 1 by 3. Here current is reduced by 1 by root 3 and torque is also reduced by 1 by root 3. So that advantage we are getting with star delta factor. Then another thing is auto transformer factor. The next it will come. Auto transformer. You know variac, 3-phase variac or single phase variac. So that is auto transformer. This is the starter mechanism at how to changing from star delta to star delta just changing. These are the concepts. Then auto transformer. Auto transformer is variac, 3-phase variac. So in 3-phase variac, we can vary the voltage from 0 to rated voltage smoothly by varying the knob. Vary by 3-phase variac. Suppose we are starting from 0 and going to rated voltage. In the process, at any time our voltage is x times the voltage, x times the phase voltage. So thing is, in variac we can slowly increase the voltage from 0 to rated voltage, so that starting current increases smoothly. No need of high there will be no huge inrush of current. So when we apply voltage x times the phase voltage, x is less than 1, obviously x is between 0 and 1. When we apply voltage x times the phase voltage, what happens to the phase current? Same thing, current is x times phase current. Okay, so what happens to the torque? Torque is x square times x square times. If the phase current is x times this and the machine is delta connected, most of the machines are delta connected, what happens to the line current? Here we are not using star, but we are using delta only because machine is delta connected. Phase current is, because phase voltage is reduced by the factor x times, phase current is reduced by x factor x, but line current will be x square times. So phase current is reduced by factor x, line current is reduced by factor x square, and torque is reduced by the factor x square times. So this is equivalent to star delta starter, where x square equal to 1 by 3.
The line current how it's
You see, delta connection, okay, delta connection, the phase current will depend upon the phase voltage. Phase voltage is x times, phase current is x times. What happens to the line current? Root 3 times, root 3 times. Root 3 times, no, that is your big, no, sorry. What, interesting, you asked the question, I am thankful for that. It is not like that. You think the transformer theory, V2 by V1 equal to X equal to I1 by I2. We are applying V2, that is X times V1. Okay. So because phase voltage is X times, current is X times. Now I2 is X times, secondary current of the auto transformer. This is a transformer. Secondary current of the transformer is X times. What happens to the primary current? X square times. Because this equation. So primary current becomes x square times. So primary current is x square times. This is not line current, this is primary current. Line current means line primary. Primary current is x square times. Okay. So this auto transformer starter is a fixed case of star delta starter. Star delta starter is a particular case of auto transformer starter where x square is 1 by 3. Here you can have any value of x from 0 to 1, whereas in auto transformer you have only x equal to 1 by 2. 1. So star delta starter and auto transformer starter. Next one is rotor resistance starter of slip ring induction motor. So if induction motor is slip ring induction motor, then rotor terminals are available. Then in rotor side, we can use rheostats for the 3-phase, and at the starting point, at the time of starting the motor, the rheostats in the rotor circuit are kept at the maximum value. Okay. If the rotor circuit resistance is maximum because rheostats are added at the slip ring, the rotor current will reduce. If rotor current is less, obviously starter current will be less, because starter current depends upon rotor current. Rotor current refers to stator, and plus no load current is the starter current. So when we put rheostats in the rotor circuit through slip rings, so rotor current reduces, so starting current also reduces. And the characteristics, you know, yeah. This is what these rheostats are used for starting. This is the equation. This is okay. This graph you see. So for different values of resistances, the torque speed characteristics of induction motors are like this. So if we put more resistance, the starting torque increases initially, then maximum torque is obtained at the starting. After that again it decreases. You see, that point you should remember. So initially we started with this small R2, that with small R2, that is without any external resistance. This is the graph. We add one resistance, we get this graph. Starting torque increases. We add another resistance, starting torque further reduces. So you go on increasing like this, and so you get maximum torque at the starting. So if it increase further, if you increase the resistance beyond that, again starting torque will reduce. So maximum torque will not be obtained. You are telling this point should be here. No, I am not. This starting torque should be 0. If the static, it is not why it is not starting. That is what I am telling. Your point is why the starting torque is not 0. First thing, if the starting torque is 0, motors will not start. Motor will not. If the starting torque is 0, motor will not start. Actually, single phase induction motors starting torque is 0. But fan motors, your domestic fans in your house, so they are single phase induction motor. Their starting torque is 0. But if the starting torque is 0, motor will not rotate. So that is a headache for how the motor will not rotate. What is the use of? So to have a starting torque, we are putting capacitors. We are putting capacitors and auxiliary winding for to give the starting torque. The starting torque will be 0, then that is a motor will not start. And why the starting torque should not be 0? Starting torque should not be 0 first. Then if you are applying a voltage and current, if you are applying a voltage, motor will draw current. Because current is there, torque will be there. So it is starting on what value it will start. It will start from here, here or here. It depends upon the current drawn. When, okay. Starting torque should be as high as possible. Starting torque should be
resistance and torque are proportional to each other. More will be the resistance, more will be the starting
torque. That is what. That is what it is shown in the graph. We are increasing from this is without any extra resistance. This is with extra resistance. By increasing the extra resistance, starting torque is increasing.
Due to the inertia, it will not start.
It will not start. That is what.
If the inertia rate of the
Yes, that is one important point. That is one important point. Inertia should be inertia also decides the torque. So big, if the motor size is bigger, then inertia will be more. With more inertia, starting it requires more starting torque to for increasing the speed.
that is that way, so there is a torque image on
Turns. Speed is given by the factor.
So the torque is inversely proportional to the speed. Yes.
No, it is not like that because you have E here. E is dependent on speed. Basically you want to know the torque speed relation. Okay, I just mentioned that. Again I am repeating. Just I mentioned. No, this is not a direct equation because what is there in the torque equation? The numerator E is there. E is the back EMF. Back EMF is dependent on the speed. So it will be better if you write the torque equation in terms of voltage and slip. So that is what I am going to explain. You can right now you can try to understand. You recall the equivalent circuit. In the equivalent circuit, you have a resistance R2 dash by S. In the rotor circuit, this represents the power, torque and mechanical power. So this resistance into I2 dash square. This is the current is I2 dash and torque resistance is this. So this is the power. And this is for one phase. For 3 phases it is multiplied by 3 phases. And this is the power by speed is the torque. What is the speed?
2 pi
Omega S. So this is the torque. This is the torque. Alright, this is the torque expression. Now what is I2 dash? I2 dash is nearly equal to I1. If you neglect the no load current, which is no load current is less than 10%. So I2 dash is nearly equal to I1. And what is I1? From the equivalent circuit, I1 equal to V1. Voltage applied to the stator divided by total impedance. Total impedance is what? Square root of R1 plus R2 dash by S square plus X1 plus X2 dash square. This is the I1. So this I1 is substituted in here. So you will get the torque equation.
Right here, plotting the graph, P. So what will be the general equation that you keep in mind? This equation.
This equation. That is what I am writing. So this is what. So in using this equation, you write TE, torque expression. So 3 by omega S into I2 square. I am putting this. That is V1 square divided by square of this. So it is R1 plus R2 dash by S square plus X1 plus X2 dash square. This is the denominator into R2 dash by S. So this is the torque expression in torque in Newton meter. How to get the characteristics I am explaining. These days it is very easy to write a program in MATLAB thing. So what you can do, slip. This slip you vary from 0, you start from 0 slip and with steps of 0.001 and you increase up to 1. Okay, that means between 0 to 1 you have taken 1000 steps. Between 0 and 1 you have taken 1000 steps, each of length 0.001. So you start from 0, then it increase like this, like exponentially. And various 1000 steps. Between 0 and 1 you have taken 1000 points of slip value. Loading condition. And with this slip you calculate for each value of slip, you calculate TE and plot the graph. Torque versus slip. Torque versus slip, both are dependent. Torque versus slip. If you start from 0, it will be like
It's going to be a gradual increase, not a sudden increase. We are going for a gradual increase. By minimizing the
So we get points to get the characteristics. So this is the slip equal to 1 and this is the tacking torque. This is the synchronous speed because slip is 0. So you get 1000 points and you draw a graph, you will get a characteristic like this.
Then at that point, it will be probably and on which condition it will occur.
I will come to it later. This part is over. Starting mechanism over. Rotor resistance starter is over. Speed control. After starting speed control, then 30. Oh, speed control will discuss. Speed control. This is the equation it is written. The speed is given by synchronous speed into 1 minus slip. And synchronous speed is 128 by T. And slip speed is S. So this is the speed expression. So one method of speed control is by varying the frequency. By varying the frequency. If the frequency is 0, then speed is 0. As you go on increasing the frequency, speed increases. Okay. Then how do you vary the frequency? By feeding the motor from an inverter. If you are feeding the motor from inverter, through inverter gives you variable voltage, variable frequency supply. So through inverter, frequency can be smoothly varied from 0 to maximum speed, whatever allowed, and speed will go on increasing. So that is very easy method of speed control these days, because these days inverter price has gone down. At the time when inverter price was large, costly, so that was not applicable. But these days inverter prices have gone down, so with inverter it is easier to have speed control over a wide range because the speed is directly proportional to frequency.
There is a control from the stator side.
Control from starter side, rotor side. Yes. The starter side. So what are the starter side control? So there are basic three techniques are mentioned. By changing the rotor circuit resistance, only slip-ring induction motor you can apply. Then supply voltage means supply voltage magnitude you can change, frequency also you can change. Then by injecting voltage in the rotor circuit, that is again for slip-ring induction motor. First and third method are for slip-ring induction motor, and only for slip-ring induction motor, first and third method. And middle one is applied to both slip-ring and slip-ring. Then what is stator side control? Stator side control, we can control the stator voltage, stator frequency. V by control also comes to variable voltage, variable frequency. Then pole changing method. Pole changing method are not used these days, it has become obsolete. Because changing pole is more costly, but rather inverter is very low cost. So pole changing methods are not being used. Then rotor side control, you can have control from the rotor resistance, you can control inject another voltage in the rotor circuit. Then you can have cascade control, just controlling the supply voltage. Supply voltage is controlled where the supply voltage, because voltage, as you vary the voltage, torque is varied. In this equation, as you vary the voltage, torque is proportional to square of the voltage. So because this torque is dependent on the load torque all the time, this torque is equal to load torque. So when you vary the voltage, then slip will vary, the speed will vary. So how does it vary? So that is what I am. Suppose this is for the rated voltage condition, this is the characteristics. Okay, rated voltage. So you can only reduce the voltage, you cannot apply higher voltage, you can only reduce the voltage. So this is the sleep at which maximum torque occurs. If you reduce the voltage, the graph will be like. Okay, two different voltages. By reducing the voltage, the graph changes like this. So suppose you have a load torque like this. Load torque like this. So at this speed, this is the torque. At this speed, this is the torque. This is the load torque. So for different voltages, you get different speeds.
Change the voltage at a higher change of torque.
Yeah. Voltage variation of a wide range reduces only. No, what is your point?
Directive something V square, na?
V square. हाँ.
Small change of voltage, the torque will be high.
Torque will be high. The graphs are drawn like that. Same thing. Voltage variation. Rated voltage. This is the top one is the graph. Voltage is reduced by 10%. If you apply 80% of the voltage, the graph changes like this. This method is particularly used for single phase induction motor control like fan motor, fan motor or voltage control. Then frequency control I have already mentioned. Frequency is controlled from inverter. So whenever motor is supplied from inverter, you can control the frequency. Then V by H control strategy is there that we should discuss. Discuss about V by H. Okay, what is V by H control? Very popular skill which everyone should know. That is V by F control. So when we control the induction motor from the inverter, you can vary the voltage and frequency both. But there is a limitation. Suppose at a rated frequency, F rated frequency, we apply rated voltage and we get torque, speed, everything rated condition. So you want to reduce the speed. So for reducing the speed, frequency is decreased. To reduce the speed, frequency is decreased. If we decrease the frequency, I am writing small l here, though I wrote capital L here. So if we reduce the frequency, keeping the voltage constant, we are reducing the frequency to reduce the speed, but we have not changed the voltage. So what happens? Flux will increase. Because in induction motor, the voltage equation, applied voltage is nearly equal to root 2 pi, which is 4.44, frequency into flux into turns per phase into winding factor. This is the voltage equation that you can derive. F is the frequency, phi is the flux per pole, and turns per phase and winding factor. So voltage V is, we have kept constant. We have kept constant voltage at the rated value. So product is constant. If frequency reduces, then flux increases. When the frequency is rated, voltage is rated, flux is rated. Fine. But from that we have reduced the frequency, the flux increases above the rated value. If the flux increases above the rated value, there will be saturation. With the saturation, what happens? It draws more current. Current increases. Current increases means I square R losses increases. Because of saturation, iron losses also increases. Under saturation condition, core losses, iron losses also increase. And then current will be non-sinusoidal. In saturation, more and more saturation, current will be non-sinusoidal. Harmonic will come. So harmonic losses will come. Then humming sound will be produced. So there are many disadvantages when there is saturation of the core, saturation of the flux. So the saturation should be avoided. So for avoiding the saturation, flux should be maintained at the rated value, because that is the best condition if flux is maintained at the rated value. This equation. Voltage, this is the equation.
Voltage is constant.
voltage, this product is constant. The voltage is constant. Turn number of turns per phase is constant. Winding factor is constant. So only variable F and phi. So if voltage is constant, F and phi product is constant. So flux is inversely proportional to frequency or
Hyperbolic.
hyperbolic. So when frequency reduces, flux increases. That is the problem. So flux should be maintained constant at the rated value. So for maintaining the flux constant at the rated value, the V by F ratio should be maintained constant. Because flux is constant, so V by F in this equation, V by F is constant, then flux phi is also constant, which is the rated value. So that gives the best operation. So V by F ratio should be constant. So suppose like we have reduced the frequency from 50 Hz to 20 Hz, then voltage should be also from 400 Hz volt to proportionately it should be reduced. So flux should be constant. That is V. Okay, we will take a break and after that we'll.
Just press escape. 130 seconds.
ক্যামেরা সাউন্ড রেকর্ডিং করছে সাউন্ড রেকর্ডিং
टेलीकास्ट कर एक्सपोर्ट टेलीकास्ट कर एक्सपोर्ट नहीं देता हूँ किस चीज की टेलीकास्ट हो
English medium dia orang masyarakat orang Indonesia. Oh, iya, ada. Dan Indonesia kan baru kali
कहाँ से अनकनेक्टेड हाँ अरे सुनो ना ये नहीं कर रहा अनकनेक्टेड नहीं है अनकनेक्टेड देखो चेड़ा जो बने नॉर्मल स्क्रीन पे वो जो किसी से कनेक्टेड है ना तो ये अनकनेक्टेड मोड में चेंज है अरे कंप्यूटर का लॉक नहीं चाहिए मोड का अनकनेक्टेड बने के प्रोजेक्ट करना ना सिर्फ मेरा दो स्टेट है जो मेरा अनकनेक्टेड जैसा अब वो हाँ कीबोर्ड से जो ब्लैक एटम मिनी प्रो आए तो ब्लैक इसी पर जो इसी पर हमारी टिकट लगी हाँ बदल लाइट ब्लू देखना पड़ती अरे नहीं मुझे वेरिंग लिखो ना टाइम এটা আমি নতুন ক্লিক করছি এটা আর এই ওয়ানটা এটা আপনি এটারে ক্লিক করছি আমার আপনাদের ব্যাপারটা কোনখানে কোথায় মানে ইলেকট্রনিক্স এর हाँ प्रोग्राम किसका
जी ये तो आपने ये पेरिंग ये वायरलेस मीटर प्रोजेक्ट करें
नहीं इधर बैठ के लोगे क्या होगा
हाँ हाँ क्या करते हैं डिजिटल में कनेक्ट करके
विंडोज 3 की मतलब कंप्यूटर डुप्लीकेट कर रही थी ना सिस्टम कर रही थी डुप्लीकेट कर रही थी
ठीक है आइए ठीक है मैं अभी ट्राई करता हूँ फिर वीडियो कॉल कर सकते हैं बातें जब लिंकिंग करे लेकिन ये इधर से कनेक्ट कर हाँ
Kalau kayak itu banyak ada.
iya ada
Ini kali bukan poin kuliah di ada di kayak kan juga
ठीक है अभी हम मैनेज कर लेंगे बट अगर खत्म हो गया तो होगा
Hello, hello, check, mic testing. 1, 2, 3. Hello.
Maximum torque is now here. So this is it.
The power depends upon the voltage and multiplied by current.
Power equal to 3 phase current into power factor. So if voltage current both are constant, power is constant. That is constant power operation. Below the rated speed, current is constant at the rated value, but voltage is increasing linearly. So power is increasing linearly. The other way you can say power is product of torque and speed. Torque and speed. So when power is increasing linearly, torque is constant, speed is increasing linearly. So you are varying from frequency from 0 to rated linearly. So speed is also increasing linear. So the principle of speed control by rotor resistance we have discussed. For starting purpose we have discussed. This is the set of torque speed characteristics for 3 different rotor resistances. Now, if you see, if the load torque is maintained constant for different values of resistances, you get different speeds. Isn't it? You draw a constant horizontal line, constant torque line. So for different resistances, the intersection point will be different. So speed you get different speed operation. So by varying the rotor circuit resistance also, speed can be varied. That is the principle of speed control by varying the rotor resistance. Poor efficiency, poor speed. Because there will be losses in the resistance, efficiency is poor. Then speed control by cascade method. Cascade method, we are connecting two methods, two motors in cascade. Cascade means, suppose you have two slip ring induction motor. One induction motor starter you connect to the supply. Okay. And the rotor terminals are there, slip ring induction motor. That rotor terminals you take and feed to another induction motor starter. So you get different speed operation. And they are cascade, this is cascade connection, and they are coupled on the same shaft. So resultant torque will be sum of the torques or difference of the torque. Depending upon whether both torques are, if both the torques are in the same direction, resultant torque will be sum. If the both torques are in the opposite direction, resultant torque will be different. So you can have different operations, speed operations. It is shown here. The motor 1 is directly connected to supply. Then its slip ring is terminal are taking supply and feeding to motor 2. Okay. Now motor 2 is getting supply from the, so if the motor 1, motor 2 torques are in the same direction, you get higher torque. If they are opposing, you get lesser torque. It is not that you require a high torque always. According to speed requirement, if you want low speed operation, it should be subtracted. This provision can be done. This is another connection, two motors and their slip ring terminals are connected like this. Motor 1 slip ring terminal are connected to motor 2 slip ring terminal. Since motor 1 slip ring terminal feeding power to motor 2 to starter. Then the rotor side is substituted. No, slip ring terminal, stator sides are connected by resistance. These are the stator terminal. Stator terminals of the motor. Instead of connecting them to supply, they are connected by resistance.
Variable resistance.
Yes? Variable resistance. So motor 2 is getting power supply from the slip ring of motor 1. From slip ring of motor 1, motor is getting supply. Starter side is connected. So role is reversed. Stator for motor 2. Stator rotor, their role is reversed. So stator side we give supply, but we are not giving supply. We are connecting like rotor slip ring terminal. And rotor side we connect here, but we are giving supply from the motor 1. So,
From there, you can change the resistance.
Then machine 1, machine 2, these are different, same thing. Principle is same. Then another point is speed control by injecting voltage in the rotor circuit. This question you asked, that I will tell you. Today I will take time to explain. Fluid control by injecting voltage in the thing. Okay. I will explain first the principle and how it is done. Okay. You consider the equivalent circuit of the induction motor. I will start from the equivalent circuit. So I am drawing the circuit. So this is the stator resistance, stator linkage reactance, R1 and JX1. Then this side is rotor. You have JX2 dash, and we have resistance R2 dash. R2 dash. And you can put the magnetizing reactance here. JXL. Here you have applied the stator voltage. It is drawing the no load current, and this is the stator current I1. This is stator parameter. This is rotor parameter, rotor resistance and inductance. And here we put the load. If we are putting mechanical load on the shaft, you put it equivalent resistance, load resistance here. Instead of that, now let us put another source here, AC source here, another AC source here. If you are putting load, the load is taking the power, load is absorbing the power, and depending upon the load requirement, speed is varied. Now if we put another source here, this is for AC source. It can be, suppose its voltage is like this. This is plus minus polarity VN. Like phase neutral, you write. Phase is plus, neutral is minus. You put like this. So this is AC source, this is plus minus. And its current is, this is VR voltage of the source, and this is the current IR of the source. So what is power taken by this source? Power taken by this secondary source. P2 I am writing. P2 equal to voltage VR, its current is IR, and some phase angle between this power factor cos phi. For one phase, if it is a three phase, then there will be three times. This is the power. So now the power P2 associated with this source in the slip, obviously this is the slip ring terminal. This is applicable only for slip ring induction motor. So depending upon value of VR and IR, the power P2 can vary. Power P2 can be positive or negative. That means the source can give power in more power to the rotor, or it can take power from the rotor. Both are possible. This source can be act as a motor. Source can act as a motor, another motor taking power from the rotor terminal of the original motor. So in that case, you get less speed operation. Speed will reduce. You will not get higher speed. But if this is acting as alternator, supplying power to the rotor circuit, then you will get high speed operation. Higher speed operation.
How it is changing? Means whether it will let it take the power or to give it the power.
How it will
Depending on the source,
polarity of the source. So okay, that is what. So
Single phase, one phase.
this is for equivalent, for phase equivalent circuit. For three phases, you have to multiply.
Now, when you find an AC supply, that is,
This one, no?
yeah,
AC supply.
that frequency should be
Frequency should be same. Rotor frequency.
and 2 or 3 years like that.
Yes, yes. That's one. So frequency should match. So this source frequency of this AC source should be same as the rotor frequency, because you are connecting with the rotor. So how it will depend? I am telling. Suppose I am giving you an example. This is VR. You draw the phasor diagram. This is VR. The phasor diagram of the current IR is like this. IR is this, and it is drawing. This is the angle phi. So power is what? This is like it is taking power. It is taking power. So it is acting like another load taking power. Now same thing. You another instant. We make it like this. Let us say I am giving like this 180 degrees. This is IR. VR and IR angle is, I am telling that 180 degree, it can be less also. So what is voltage and current are in opposite direction. So it is giving power. It is acting as alternator. Another alternator. It is supplying power. Power is negative. In this case, power is negative. In this case, power was positive. In this case, power was negative. So it is giving power. This is IR. It can be another current here also. This is IR1 and this is IR2. Another current. So it is also has a component. This component, so same thing, it will give power to the rotor circuit. So through this controlling the magnitude of the voltage and phase angle between the voltage and current, you can control the power, whether you are taking more power from the rotor or you are giving power to the rotor. So accordingly, speed will vary.
Actually, the one thing that when the speed will change, potatoes will change, so the medium of the supply also to be changed.
That is all the time it is to be ensured that
The frequency will match with the required speed.
I will show you another scheme because you are more interested. I will show you a scheme. Just let me finish this part and I will explain. Time will be there. So I will explain how to have the matching frequency. 1:30 now. Time will be there. So this is the principle I have explained. Conventional method and static method. So the static method, in static method, the easy. Conventional method also it was done, but conventional methods are these days they have become obsolete. Conventional method I am explaining first. It is like this. You just see. This scheme is like this. So slip ring terminals of the slip. This is the original motor, first motor. This is the slip ring terminal. They are feeding power to a rotary converter. Okay, you are giving here. And rotary converter basically it has a field winding. This is DC supply. So DC supply it is giving power, producing the flux, and when you give, it produces power. Okay. So it rotor output. So it converts. Here you are giving slip frequency. Here you have slip frequency. Here you have slip frequency. Rotor frequency, slip frequency you are giving, and it is converting from AC to DC. Like this is like a DC AC to DC converter. And it is this DC power is going to the motor armature. So motor will getting supply. Motor and in the same shaft, mounted on the same shaft of the original motor. So now resultant torque will be either addition of these two torques or difference. That will depend on polarity of the DC motor supply. So you can increase the speed or decrease the speed. DC supply is getting motor from the converter. Converter is getting AC supply, slip frequency AC supply from the slip ring terminals of the original motor, and field supply is there for the rotary converter and also for the DC motor to DC supply. So this is the so whatever may be the this is one scheme. This is conventional scheme. I will discuss many other schemes are there. This is another scheme of you please see. This is the original motor, original principal motor. So these are the slip ring terminals. Slip power is rectified by the diode rectifier. This is three-phase diode is rectifier. So here you have slip frequency, slip frequency. So you get DC here at the diode rectifier. This is fed with DC motor. DC motor field supply is getting separate supply from separate source, and DC motor and this they are in the same shaft. They are on the same shaft. So resultant torque will be, if the DC motor torque is in the same direction of this, then there will be additive. If it is the opposite, there will be some difference. So DC motor is getting supply from the rectifier on the rotor.
But they will run at same speed because same start.
They will run at the same speed. Both will run at the same speed. But that same speed is more or less. That will depend whether torque is additive or subtractive.
The variation in frequency will not matter much because that will be very small part of it. At best, it can cause some harming in the machine, but it will not damage the machine as a whole. So,
Actually, frequency part variation is not coming here because this is the supply frequency. Slip frequency. Slip frequency are making DC. So that doesn't make. static member system, it is another scheme. This scheme I was also going to explain. This is another scheme. This is the another one scheme. This is second scheme. So here again, this is the original motor, slipping induction motor getting supplied from the three phase mains. Then the rotor terminals, slip frequency AC, converted from AC to DC by diode rectifier. This is the DC link. Then this is one inverter, three phase inverter. And inverter, these are the input terminals. Input terminal, they are connected from the three phase mains. Three phase mains to transformer, then transformer connected to inverter AC side. Okay. So in this case, this inverter firing angle is more than 90 degree. So slip power is rectified from AC to DC. DC current is flowing in the direction as shown from this direction. So it is going power, and it is giving power. DC link is giving power, means motor slipping terminal giving power. And this side, this is DC, this is plus minus. So DC should be plus, DC should be minus. You are feeding current ID, so ultimately you are feeding power to the DC. So at the DC terminal of the inverter, you are feeding power, and ultimately you will get power from at the AC terminal, and which is going to the supply. This is the conventional, similar principle only. Draw another figure, the slipping terminal, total converter, similar scheme. That's another figure. This also we discussed just now, same thing. So you can have subsynchronous speed control, supersynchronous speed control, everything is possible. Whether we are giving power or taking power. This is a numerical. Numerical you can do later on. Numerical. You consider DC generator. So DC generator, it is giving DC supply. You are getting DC supply at the armature. You are getting DC supply. What about the current in the conductor? Is it direct DC or AC? Current in the conductor is AC, but at the external circuit you are getting DC. How we are getting this? Because of the commutator and drop. Something. Okay. So if there is no commutator, then conductor current is stator side. Conductor armature current is AC and external circuit current is DC. So same thing is here. There is no commutator. Actually, these days these have become obsolete, so they are not taught. Very long back. Even we have not studied. We are not graduated in '89. So that time also rotary converter was not taught. But our professors, they mentioned about the rotary converter, gave some idea because they have studied during their time. So our professor was very senior. So they taught us how rotary converter was there. So we, out of interest, we learned something about rotary converter. But these days also nobody is using that. Because power tonics, what is other options, power tonics, inverter, etc. They have taken over, so rotary converter has no interest. From base to UC Burla, that is University College of Engineering Burla. Burla.
These later on came to idea and he doctor chair and we see what I will. Sir also came. Sir, no, sir. Going from Pula to IC doctors. But Sarab sir,
Sarab sir was there in Burla. Burla, then he shifted. Baby Pati, sir, only his batch. He is junior to me. It means young age, batch wise, he is junior to me. Vijay Panikray is from CET Boni. Sukumar Mishra, he is from Burla. Sukumar Mishra, AK Pradhan, they are from Burla. Okay, so now these Partonic converters are taken over, so rotary converters have become obsolete. So this, then we'll go to breaking. So we started with circle diagram. After circle diagram, we discuss about starting. Then we discuss speed control. You start the motor, then do the speed control, then do brake. Wherever required, you have to apply brake. So braking is also one important control aspect. Braking, there are three types of braking. Three types of braking. First is regenerative braking, then dynamic braking, then plugging. Three types. In regenerative braking, the machine operates as generator. Say induction machine. Induction machine, if sleep is between 0 and 1, it is motor. Induction machine, if sleep is between 0 and 1, it is motor. If sleep is less than 0, means negative, less than 0 means negative, it is generator. If sleep is more than 1, it is braking, pre-operation. So generator itself is a braking, because motor and brake, two things, motor and brake. Motor, the torque and speed both are in same direction. Increase in the torque means increase in the speed. But in braking, torque and speed are in opposite direction. Braking. So regenerative braking means where the machine is operating as a generator, torque and speed are in opposite direction. So in regenerative braking is also regenerative generator operation is also another form of braking. That is you get generative braking, regenerative braking. Okay. So in regenerative braking, the induction machine operates as a generator. That means sleep is less than 0, negative, and speed is more than the sleep is negative means speed is more than the synchronous speed. That also you know, when the induction machine is driven at a speed higher than the synchronous speed, it operates as a generator and feeds power. So you have to drive from the shaft. You have to provide torque, power input at the shaft at a speed higher than the synchronous speed, and it will feed power to the AC source, operating as a generator. And this is generative braking. Then another is dynamic braking. Dynamic braking means rheostatic braking. Rheostatic braking. Okay. So say generator. Generator is giving supply power at the terminals. If the supply is cut off and you connect external resistances, then power will be dissipated in the resistances. Whatever power generated by the generator, instead of taking away from the source, if you disconnect from the source and connect extra resistance, then power will be dissipated. It will be operating as a generator, but instead of feeding to the source, it will be dissipated in the resistance. That is the rheostatic braking, means dynamic braking. Then another is plugging. Plugging means you plug. In plug you connect whether like this or you interchange. It is same thing, similar thing. Okay. So plugging means changing at the plug terminals. So what plug terminals? In induction motor, say phase sequence is RYB. RYB. If you interchange any two terminals, the phase sequence instead of RYB will be RBY. If phase sequence becomes RBY, then the magnetic field will rotate in the opposite direction. The magnet, initially you start as you are operating as a motor, so magnetic field was rotating in the same direction as the rotor. When you interchange only two terminals, phase sequence reverses, magnetic field rotates in the opposite direction. When the magnetic field rotates opposite direction to the rotor, then it is braking. That is plugging. Then dynamic braking has some variations. Dynamic or rheostatic braking, like DC dynamic braking or AC dynamic braking or capacitance braking, zero sequence braking, there are variations. So regenerative braking I have already explained. Regenerative braking, machine is operated as a generator. You give power input to the shaft through prime mover, and it operates as a generator and feeds power as a generator. So it is regenerative braking. This is what? So this part, this is the speed versus torque. This y axis is speed, x is the torque. This is the starting torque and this is the synchronous speed. The motoring operation is here. If the speed is more than the synchronous speed, it will act as a generator. Plugging I have already explained. Plugging, you know the slip equation. Slip equation is given by Sn equal to synchronous speed minus motor speed. At the synchronous, when you change the phase sequence by interchanging two terminals, this magnetic field rotates in the opposite direction. So instead of plus omega ms, you write minus omega s because it is rotating in the opposite direction. So now slip is 2 minus s, more than 1. So speed it is braking operation. Magnetic field is rotating in opposite direction to the rotor, so you get braking action. So that is not shown here. You see, when you change the phase sequence and you leave it like that, after some time motor will rotate in opposite direction because you have changed the phase sequence. Motor will rotate in the opposite direction. That is called reverse motoring. Direction of reversal occurs. Direction of rotation reversal. So initially this is the speed versus torque graph. So this is for motor forward. This is for the forward motor. Now when you change the phase sequence, you get reverse motoring. Reverse motoring is less minus synchronous speed, and this is the graph. Okay. So if you extend it for a slip more than 1, this is the graph. So when you do the plugging, operating point changes, you get in this region braking, in this plugging braking, and then it goes to reverse motoring. Is it okay? That was plugging. Then AC dynamic braking. AC dynamic braking is like this. In case of motor, whether squirrel cage motor or slipping motor doesn't matter. So these are the 3 terminals. This is for motoring operation. All 3 terminals are connected to 3 phases. Now for braking operation, you open one terminal, so that now you apply only one phase is disconnected. A is disconnected from the supply. So ultimately what you are doing, you are getting a single phase supply. Single phase supply. With single phase supply, you get a braking action. Other option is like this. You connect A and B together. So there is again another single phase, but only connection is different. This is 2 lead connection, this is 3 lead connection. So you get dynamic braking, and why if it is a slip ring induction motor, in the rotor side you can put resistances, and we get speed variation over a wider range. If it is only squirrel cage motor, this is slip ring induction. If it is squirrel cage motor, means it is short circuited only. But in slip ring induction motor, we have this additional advantage. That was AC dynamic braking, 2 lead connection or 3 lead connection of stator. Second is DC dynamic braking. In DC dynamic braking, the supply stator terminal is disconnected from the stator terminal, disconnected from the AC supply, and you apply DC supply like this. These are the stator terminals, A, B, C are the stator terminals. You apply DC supply like this or this or this, any circuit you can follow. So in this case, what you are doing? You are feeding a direct current to the stator. You are not feeding alternating current. You are feeding direct current. If you feed 3-phase alternating current, rotating magnetic field is produced. But if you are feeding direct current to the stator, rotating magnetic field will not be produced. It will be stationary, standstill magnetic field. Standstill magnetic field is produced, but rotor is rotating because of inertia. During motoring operation, it was rotating due to same inertia, because after braking also it will continue to rotate. Now what happens? Initially motoring operation, magnetic field was rotating and motor was rotating at a little less speed in the same direction. Now motor is rotating, but magnetic field is stationary. What happens to the relative speed? It is negative, isn't it? Because the magnetic field is 0 speed, so relative speed is 0, negative. Because relative speed is negative, the induced current, EMF and current will be in opposite direction. So that will keep breaking down.
rotor winding or stator?
Rotor winding. DC motor has also back EMF.
distance, no vacuum, like equilibrium.
Counter EMF will be there. Because flux is there and motor is rotating, the back EMF will be there. Okay. This is dynamic pressure.
Two lead supply, three lead supply, two lead supply. It is due to the synchronism, obstruction of synchronism, so that it is going for breaking condition.
Right.
Why we are doing this two lead supply? Two leads are providing this.
So this is AC dynamic braking. Purpose of braking is to reduce the speed and maybe to stop the motor. Okay. So when you want to reduce the speed, so in AC dynamic braking, you disconnect one phase. If you are disconnecting one phase, you are reducing the power input. If you are disconnecting one phase, you are reducing the power input. Instead of three-phase motor, you are operating like a single-phase motor. It will have less power, so speed will reduce. And braking action you get because of the characteristics. If you understand, characteristics are not here. I will explain.
This is after
The
the
resultant magnetic field will be decreasing. If one
You see, in single phasing case, B and C single phasing case, this is when you describe it, it is like a single phase induction motor. You are giving single phase supply only, P and N are there, single phase supply. So now we will understand what happens in a single phase induction motor. In single phase induction motor, you are giving single phase supply, same thing applies here. When you give a single phase supply to a winding is basically what? Winding is equivalent to an inductance, and you are feeding one alternating current. So what happens? In the axis there is a flux which is alternating, varying sinusoidal. Current is I sin omega t, flux is also n I sin omega t. It is not rotating magnetic field will not be produced. In case of three-phase induction motor, rotating magnetic field is produced. I have explained. But in this case, it is not a rotating magnetic field. It is only time-varying magnetic field. Okay. So that's pulsating magnetic field. And pulsating magnetic field, and because motor is rotating, there will be torque. So you see, this pulsating magnetic field is equivalent to two magnetic fields rotating in opposite direction. How I will tell? Let us consider. I will draw. Let us consider two coils. Okay, two coils. So magnetic field of both the coils is there. Magnetic. I am talking about MMF. MMF equal to N into MMF equal to N into. Let us consider two coils. Their MMF at the time omega t equal to 0. Time t equal to 0. Both are in same direction. Two fields, two coils. So their MMF is in the same direction. Resultant MMF is addition. So it is given by this bigger. The radius of the inner one is half. So twice it is become double. Then after that, this is two lines are there. One is rotating in the forward direction, in this direction. Another one is rotating in the opposite direction. Two are rotating in the opposite direction. So at time omega t1 equal to theta 1. After time t equal to theta 1. So what happens? This is 1. The two fields which are in the same direction at the time t equal to 0. Now both are in opposite direction. Now what is resultant of these two? Their horizontal component will cancel. Only vertical component will be reducing in the same direction along the same axis. But it has reduced. So initially it was maximum, some f value here, maximum value. Now at this point it is something 2 into Fm cos theta 1, Fm by 2 into cos theta 1. Both are Fm by 2, Fm by 2, Fm by 2, Fm here. Now Fm by 2 cos theta 1 for 1 into 2. Okay. So with that it will reduce, finally it will come to 0, then it will return in the opposite direction and it will become a negative maximum. So this is what you get here. This is a pulsating magnetic field. This pulsating magnetic field is equivalent to two rotating magnetic fields. Both are of same magnitude or rotating in the opposite direction. 180 degrees. Opposite direction, rotating in opposite direction. So this is what you get in single phase induction motor, fan motor. One single coil will not give a rotating magnetic field. We have two coils. They are separated by capacitor. So two currents you get phase split. So now when two magnetic fields are rotating in the opposite direction, what happens? Two torques are
Double field working.
double.
In this case, the complete connection and delay, the motor is not stop, speed is not zero.
Speed will not be
You have to apply mechanical.
mechanical brake.
Yeah, after so this, you have to apply mechanical.
Yes, mechanical brake has to be done. So let us draw the speed versus torque graph. Now, what we have seen, we have two magnetic fields, they are rotating in opposite direction. For the one which is rotating in the forward direction, for that, torque versus speed graph will be like this. This is the speed torque characteristic due to the forward field, corresponding to forward flux. Now, for the reverse one, we have like this. For the opposite rotating one, this is due to the backward field. So at time t equal to 0, here, whatever these are equal and opposite, resultant torque is 0. This is plus side, minus side, resultant both are equal and opposite, resultant torque is 0. So starting torque is 0. But at any other speed, say resultant of these two means addition of these two, it will be like suppose starting torque is 0, at any other speed torque will be there. So in this region, the speed and torque are in opposite direction, so you get braking action. Similarly also here. So this is what you operate here during dynamic braking, you operate here. Okay. I will move forward. Is over almost. Okay. This part is over. Okay, if you have any other question, you can ask.
Compared to separate.
So we are comparing induction motor with a DC generator. Okay. DC motor. Okay. DC motor. DC motor. So this is speed versus torque. So speed torque characteristics of the DC motor, shunt DC motor, is like this. If you increase the torque, speed reduces. If for an induction motor, it will be like this. This is for induction motor and this is for DC motor. Okay, similar, characteristics similar. Only thing, this part in induction motor is only for the starting part, starting transient. After starting transient, this part is not there. So characteristics are similar. But problem is where your point is why induction motor it is poor, why DC motor is not poor. Because in DC motor, you are giving supply voltage to the armature. You can easily vary the armature voltage. If you reduce the armature voltage, graph will be different graph you will get by giving different voltage. You vary the voltage applied to the armature, you get lot of variations like this. But in induction motor, similar thing is not there. In induction motor, only thing you vary the frequency. In induction motor, if you can vary the frequency, you give another frequency and you will get another one like this. But for that you require an inverter. Inverter for induction motor you can operate like DC shunt motor. If it is not inverter fed, directly supplied to supply, you will not get this part. You have only one. So range of speed variation is only limited. But in DC motor you have range of speed variation is wide. That up. First of all, in a transformer and induction motor, whose power factor is better? Why?
Static, no loss is very negligible. Here, the air gap is more, and that is why the yoke loss is also there. Many losses come into picture. So
That is fine. Good answer. So that is the point. In transformer, there is no air gap. So both the primary and secondary of the transformer are linked by only iron core. In iron core, reluctance to the flux, it doesn't oppose flux, doesn't oppose much. It provides some reluctance but not much reluctance. Because how do you define reluctance? I'm defining reluctance equal to like resistance L by mu 0 mu r A. Okay, mu 0 mu r A. For iron core, this mu r is of the order of 1000, 10,000 like that. Mu r. So reluctance is small. Reluctance means so compare if there is only if you consider compare with air mu r equal to 1. So compared to air, iron core 10,000 less, 10,000 factor less. So reluctance is less. But in induction motor there is air gap. Primary means stator, secondary means rotor. Their iron core is there, but in between both are separated by air gap. Because of the air gap, the reluctance is more. Okay. So induction motor takes more magnetizing current compared to DC motor because higher reluctance. It produces the same flux. It takes more magnetizing current, and this magnetizing current makes power factor poor. For example, if you draw the phasor diagram. So this is a voltage. This is the voltage. This is the no load current ID. Okay. In transformer, this no load current is less because iron core. But in induction motor, no load current is more and this power factor is also very poor, up to 90 degrees. So because of this, induction motor has poor power. Thank you. I also appreciate your participation. So much active, so much questions, so much interest. So I also enjoyed talking. When participants participate actively and put in cast questions, it is really interesting. And thank you for your